Right now, at this very moment, two machines the size of a small car are drifting through the darkness between stars. They have no fuel left to change course. No one can fix them. No one can reach them. And yet, they are still talking to us. Launched in 1977, Voyager 1 and Voyager 2 are the farthest human-made objects ever to exist. They have crossed a boundary that took billions of years to form and 4 decades of flying to reach. And what they found on the other side? Nobody predicted any of it. A wall of plasma denser than anything in our models. Temperatures that should be physically impossible. Particles racing at speeds that defy explanation. And a sound, a deep, persistent hum coming from a place that should be completely silent. These two spacecraft have shattered virtually every prediction scientists made about the edge of our solar system. And if you think space is just a cold, empty void, what Voyager found is about to change your mind forever. If you want to explore what lies at the absolute edge of everything humanity has ever touched, hit that like button and subscribe right now. Because what these machines discovered out there changes how we understand our place in the cosmos. Let's begin. In the summer of 1977, NASA launched 2 spacecraft with a modest ambition: fly past Jupiter, photograph Saturn, and drift quietly into oblivion. Nobody expected them to survive 5 years, let alone nearly 5 decades. Nobody imagined they would still be sending data home long after the engineers who built them had retired, grown old, and in many cases, passed away. Both Voyagers launched within weeks of each other, timed to exploit a once-in-175 years planetary alignment, a gravitational gift that allowed the spacecraft to visit multiple worlds without carrying anywhere near enough fuel to reach even one of them under their own power. Jupiter's gravity hurled Voyager 1 towards Saturn. Saturn's gravity flung it upward, out of the flat disk where the planets orbit. Voyager 2 took a longer, more elegant path. A grand tour that swung it past Uranus and then Neptune, humanity's only close look at those distant worlds, before sending it plunging downward into the void. They carried cameras, spectrometers, plasma detectors, magnetic field sensors, and something else entirely. A 12-inch gold-plated copper disc, known as the Golden Record, loaded with sounds of Earth, and greetings in 55 languages, and music ranging from Beethoven to Chuck Berry. A message in a bottle thrown into an ocean so vast that finding it would require a miracle. Nobody truly expected the Golden Record to ever be found. But the engineers built something far more durable than anyone anticipated. And now, nearly 50 years later, both spacecraft have done something no human creation has ever done before. They have left the solar system entirely. But here is what makes this story genuinely extraordinary. The journey to that boundary was supposed to be straightforward. Scientists had models. They had equations. They had decades of theory about what the edge of our solar system would look like. And from the moment Voyager began approaching that boundary, reality started proving every single one of those predictions wrong. By the early 2000s, both Voyagers had left the known planets far behind. They were now entering a region scientists called the termination shock, the zone where the solar wind, a constant stream of charged particles blasting outward from our sun at over 1 million miles per hour, begins to slow down. Think of it like a powerful river finally meeting an ocean. The current keeps pushing, but something ahead is pushing back. The first truly strange signal came from Voyager 1 in 2004. Scientists expected the solar wind to weaken gradually, smoothly, predictably. Instead, the instruments showed something that looked like chaos. Wind speed dropped, then surged, then dropped again. Over months, the pattern repeated in waves. Something out there wasn't just resisting, it was pushing back rhythmically, like something breathing. Then the cosmic ray detectors started behaving strangely. Cosmic rays are subatomic particles accelerated to nearly the speed of light by exploding stars and colliding galaxies. They rain down on everything in the universe constantly. The solar wind and our sun's magnetic field normally deflect a large portion of them away from Earth, which is lucky because these things can shred DNA and scramble electronics. As Voyager traveled farther from the sun, scientists expected to see cosmic ray levels rise smoothly and steadily. They did not. The levels spiked, then fell, then spiked again, higher. The pattern was impossible. It was as if some invisible barrier was blocking these particles, then letting them through, then blocking them again. Engineers checked and rechecked the instruments. Everything was working perfectly. The readings were real. Scientists scrambled for an explanation. The best model they could produce suggested that the edge of our solar system wasn't a fixed wall. It rippled. It breathed. When the sun is active, its wind blows harder and pushes the boundary farther out. When the sun quiets down, the wind weakens and the boundary contracts. Voyager was flying through a zone that moved, but that still didn't explain everything. The magnetic field readings were adding another layer of strangeness. As Voyager approached the boundary, the field lines, which by all models should have started rotating, shifting to point in new directions, stayed mostly the same. It was like walking through a doorway and finding yourself in an identical room on the other side. Were they even approaching a real boundary at all? Then in 2009, something happened that no model had predicted whatsoever. Voyager 1 entered a region where the solar wind slowed, not gradually, not over weeks, but within days, to zero. Not weakened, not reduced, zero. The outward flow simply stopped. The spacecraft was now drifting in a zone where particles moved sideways, parallel to the boundary. Scientists named it the magnetic highway, a corridor where solar and interstellar particles could flow together in both directions at once, like two rivers somehow occupying the same channel. This region wasn't in any model, it didn't exist in any theory, nobody had imagined it could exist. And Voyager had found it purely by going there. Let's talk about temperature for a moment, because what Voyager measured next genuinely stunned the scientists analysing the data. Temperature in space isn't quite the same as temperature on Earth. There's no air to feel hot or cold. But particles have temperature based on how fast they move. The faster they race around, the higher their temperature. In the inner solar system, the solar wind plasma registers around 100,000 degrees Celsius. Sounds terrifying. In practice, the plasma is so thin that a human being would freeze to death instantly because there simply aren't enough particles to transfer their heat to your body. But the number is real. As Voyager moved into the magnetic highway and toward the boundary, scientists expected temperatures to drop. The solar wind was slowing down. Slower particles mean lower temperatures. That is basic fundamental physics. What they got instead was the opposite. Temperatures climbed. In some measurements, they jumped to over 250,000 degrees, 2.5 times hotter than anything recorded closer to Earth. The data sparked arguments inside the mission team. Some researchers were convinced the instruments were finally failing. 40+ years in space, blasted by radiation, subjected to temperature swings from near absolute zero to the equivalent of a furnace. The sensors had every reason to be giving false readings. But then Voyager 2 reported the same thing. Same phenomenon. Higher temperatures at the boundary, different trajectory, different instruments, different part of the sky. And yet, the same impossible result. Two independent spacecraft with separate systems finding identical physics. The instrument failure theory died immediately. So what was actually happening? The answer involved two processes working together in ways nobody had fully modelled. First, compression. When the solar wind slams into the interstellar medium, the material between the stars, the particles don't simply stop. They compress, they pile up. Like cars on a motorway that suddenly hits gridlock, kinetic energy has to go somewhere. It converts to heat. The boundary becomes a zone of extreme compression, where particles collide millions of times per second, and each collision releases tiny amounts of thermal energy that add up to an inferno. Second, magnetic reconnection. This happens when magnetic field lines from different regions cross each other, tangle, and then snap, releasing enormous bursts of energy in the process. Picture an overstretched rubber band breaking. That energy doesn't disappear. It heats the surrounding plasma to extreme temperatures almost instantaneously. At the edge of our solar system, field lines from the Sun's magnetic field and from the interstellar medium were meeting, tangling, and snapping constantly. Voyager detected these bursts, sudden spikes of intense heat lasting hours before settling, then spiking again. Each one like a small contained explosion spread across millions of miles. The temperature mystery also connected to a deeper puzzle. If the boundary was this energetic and this hot, why did the solar wind stop so abruptly at a fixed point? Hot plasma should be more dynamic, more resistant. It should push back harder. Yet Voyager was finding a zone where the solar wind simply froze in place, unable to advance. The answer was that something was applying equal and opposite pressure from the outside, and that something was interstellar plasma, the thin sea of charged particles that fills the space between stars. For decades, scientists had known it existed. They had theorized about its properties, but they had never measured it directly. Theory said it would be thin, cold, and mostly invisible. Voyager was about to prove that theory spectacularly wrong. Before we get to the crossing itself, we need to talk about something that Voyager revealed along the way, something that forced scientists to completely throw out decades of assumptions about the structure of our solar system. The heliosphere is the name for the protective bubble that our Sun creates around itself and everything that orbits it. The solar wind blasts outward in every direction, pushing against the interstellar medium and carving out a region of space where our Sun's influence dominates. Scientists had modelled this bubble extensively. Their best simulations produced a shape roughly like a sphere, maybe slightly elongated into a teardrop by our motion through the galaxy, but essentially symmetrical, essentially smooth. Then the two Voyagers started measuring where they actually encountered the boundaries, and the results made no sense. Voyager 1 crossed the termination shock, the first major boundary where the solar wind begins to slow, at 94 astronomical units from Earth. 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. Voyager 2 crossed the same boundary at 84 astronomical units, 10 units closer. That gap represents nearly 1 billion miles. No model had predicted anything like this. The heliosphere wasn't round. It wasn't even close to round. It was being compressed and deformed by the interstellar magnetic field and by our motion through the galaxy. Our solar system moves through the Milky Way at 43,000 miles per hour. As we move, we plow into the interstellar medium ahead of us, compressing the heliosphere on that side. The opposite side, the trailing edge, stretches out behind us like a comet's tail. New models began to emerge from the data. They showed a heliosphere shaped like a crescent or a squashed comet with a dramatically compressed front and a stretched, possibly fragmented tail. Some simulations suggested the tail doesn't even exist as a single structure. It might break apart into multiple lobes, twisted and tangled by magnetic forces into something almost organic-looking. Radio astronomers tried to observe the heliosphere from Earth using distant pulsars, neutron stars that emit regular radio pulses, and measuring how those pulses change as they pass through our solar system's edge. The results were deeply confusing. The boundary appeared to be in different places depending on which direction you looked. It moved. It shifted. It behaved nothing like a stable sphere. Voyager's data explained why. The heliosphere breathes in sync with the Sun's 11-year activity cycle. During solar maximum, when sunspot activity peaks and the solar wind strengthens, the heliosphere expands outward. During solar minimum, it contracts. But the breathing isn't uniform across the whole structure. In different regions expand and contract at different rates depending on local conditions in the interstellar medium. And every 11 years, the Sun's magnetic field flips entirely. North becomes south, south becomes north, sending ripples of disruption cascading through the entire boundary for months. The picture that emerged from all of this was shocking in its complexity. The edge of our solar system isn't a wall. It isn't a clean boundary. It's a constantly shifting, breathing, rippling interface between two cosmic environments. And it looks nothing like what anyone imagined. August 25th, 2012. A date that will be recorded in history books for as long as humanity exists to write them. On that day, Voyager 1's instruments registered a sudden, violent shift. The number of solar particles detected by its sensors dropped by half in a single day. Not gradually, not over weeks. A cliff edge. One moment, the detectors counted thousands of solar particles per second. The next, hundreds. At the same time, galactic cosmic rays surged by 30% in hours. Was this it? Had Voyager 1 finally crossed the heliopause, the true boundary between our solar system and interstellar space? Not everyone was willing to say yes, and the reason was the magnetic field. Voyager was still detecting what appeared to be the solar magnetic field, the same orientation it had been measuring for years. If the spacecraft had truly exited the heliosphere, the field should have rotated, aligning with the interstellar field which comes from a completely different direction. But it hadn't. The field direction was unchanged. This created months of fierce scientific debate. Some researchers insisted Voyager had crossed. Others said it was still inside, just in some strange transitional zone that nobody had anticipated. Then in April 2013, the Sun solved the argument for them. A massive solar eruption, a coronal mass ejection, blasted billions of tons of plasma outward from the Sun's surface. These eruptions are common enough, but this one sent a shockwave that travelled all the way to Voyager's position and beyond. When it reached the interstellar plasma surrounding the spacecraft, the plasma began to oscillate at a specific frequency determined by its density. Voyager's instruments detected those oscillations. By measuring the frequency, scientists could calculate the plasma density directly. The density was 40 times higher than plasma inside the heliosphere. 40 times. This wasn't a marginal difference. This wasn't a measurement error. This was a completely different environment. Voyager 1 was surrounded by interstellar plasma. It had left the solar system. The crossing had happened in August 2012. The plasma measurement proved it beyond any doubt. For the first time in the 4.5 billion year history of our planet, something made by human hands had left the solar system and entered the space between the stars. But what about the magnetic field? Why hadn't it rotated? The answer was almost absurdly anticlimactic. Pure cosmic coincidence. In the specific region where Voyager 1 happened to cross the heliopause, the interstellar magnetic field and the solar magnetic field were pointing in almost exactly the same direction. The two fields were accidentally aligned, which meant there was no rotation to detect. Only the plasma density measurement could reveal the truth. Voyager 2 crossed the heliopause 6 years later, in November 2018, and told a completely different story. When it exited, the magnetic field did rotate. The instruments watched it shift direction over several days, gradually aligning with the interstellar field. The crossing happened at 119 astronomical units, just 3 units closer to Earth than Voyager 1's crossing, but in a completely different region with completely different local conditions. 2 crossings, 2 completely different experiences. Same destination. This told scientists something profound. There is no single uniform edge to our solar system. Every part of the heliopause is unique, shaped by the interplay of local magnetic fields, plasma densities, and the ever-changing output of the Sun. Here is something worth pausing on because it has direct consequences for the future of human spaceflight. Cosmic rays are the universe's artillery. They are atomic nuclei stripped bare of their electrons and accelerated to nearly the speed of light by the shockwaves of dying stars. When one of them hits a computer chip, it can flip a single bit from 0 to 1, corrupting data, causing crashes, potentially disabling critical systems. When one hits a human cell, the consequences range from negligible to catastrophic, depending on where it strikes and what it damages. The heliosphere protects us from most of them. The solar wind and the Sun's magnetic field deflect and absorb the lower energy cosmic rays before they ever reach the inner solar system. Earth itself has additional protection from its own magnetic field. Without all of this layered shielding, life as we know it would face significantly higher radiation levels every single day. Voyager's cosmic ray detectors measured this protection being stripped away in real time. Near Earth, the instruments detected around 100 million cosmic ray particles per square meter per second. By the time Voyager crossed the heliopause and entered interstellar space, that number had risen to 900 million. 9 times the cosmic ray flux of the inner solar system. This is what awaits any human mission beyond the heliosphere. And even within it, the numbers aren't trivial. Astronauts on the International Space Station, which orbits within Earth's magnetic field, already receive significantly higher radiation doses than people on the ground. Astronauts on the Moon or Mars would be exposed to the full solar wind without planetary protection, and anyone travelling beyond the heliopause would face the full fury of interstellar space with nothing between them and the galaxy's constant artillery barrage. The energy spectrum of the cosmic rays also changed dramatically beyond the heliopause. Inside the heliosphere, Voyager detected mostly lower energy particles. Outside, it detected the full spectrum, including ultra-high energy cosmic rays carrying billions of electron volts. A single one of these particles striking a critical cell could cause damage far beyond what lower energy radiation produces. And most cosmic rays originate from supernova remnants within the Milky Way. When a massive star explodes, the expanding shockwave accelerates particles to relativistic speeds over thousands of years. The galaxy produces hundreds of these explosions every century, each one seeding the interstellar medium with a new wave of artillery. Some cosmic rays arrive from even farther away, from other galaxies, from colliding galaxy clusters, from the jets of supermassive black holes. These extragalactic particles are the rarest and most energetic of all. Voyager detected a handful of them, confirming that our local interstellar neighborhood is bombarded by particles from across the observable universe. Understanding the precise nature of this cosmic ray environment, where the particles come from, what energies they carry, how they move through the interstellar medium, is essential for designing any future deep space mission. Voyager is mapping the radiation gauntlet that any ship heading for another star would have to run. And what it's found suggests that gauntlet is considerably more intense than our models predicted. In 2012, something happened that almost nobody outside the scientific community heard about, and it deserves to be far more famous than it is. Scientists listened to the sound of interstellar space, and it was humming. Let's be precise about what this means because the headline sounds impossible. Space is a vacuum. Sound needs a medium, molecules vibrating against each other, to propagate. You cannot hear a scream in space. That part is true. But plasma is not a vacuum. In plasma is matter, charged particles that interact with each other and with magnetic fields. And those interactions create waves. Pressure waves. Oscillations that propagate through the plasma exactly the way sound waves propagate through air, following the same underlying physics. You can't hear them with your ears, but you can detect them with instruments, and you can translate them into audio. When the April 2013 solar eruption sent its shockwave beyond the heliopause, it compressed the interstellar plasma surrounding Voyager. That compression created oscillations at a frequency of 2.6 kHz, far too high for the human ear without processing, but when scientists shifted it into the audible range, they heard a rising tone. A whistle that climbed in pitch as the wave passed through, lasting for months before finally fading. The heliosphere had been struck like a bell, and the ringing was audible. But that wasn't the most surprising part. When scientists went back and analysed Voyager's historical data more carefully, digging through years of recordings, filtering out noise, they found something they hadn't expected at all. A persistent low-frequency hum, around 30 Hz, not triggered by a solar eruption, not associated with any specific event, just there, constant, present in the interstellar plasma at all times. What causes this background hum? The interstellar medium itself is never truly still. It flows, carried by galactic rotation and local currents. It's stirred by turbulence, eddies and vortices in the plasma created by magnetic field variations. Distant events, supernovae light years away, collisions between interstellar clouds, some magnetic reconnection on galactic scales, send low-frequency waves propagating through the medium for enormous distances. In Voyager's location, these background waves were converging, creating a persistent acoustic texture that never goes away. NASA released audio recordings of these plasma oscillations to the public. The internet response was remarkable. Millions of people listened to the sound of interstellar space for the first time. Some found it deeply eerie. A low, toneless drone that never varies, never stops. Others found it strangely beautiful. Evidence that even in the deepest silence we can imagine, the universe is still vibrating with energy. The famous line from the movie Alien, "In space, no one can hear you scream," is technically accurate, but it misses something essential. Space isn't silent. The medium between stars hums with energy that has been travelling for thousands of years. Voyager caught it, and now, for the first time in human history, we have heard it. Before Voyager made its crossing, one of the most confident predictions scientists had made about the edge of the solar system was this: there would be a bow shock. The logic was airtight. Our solar system moves through the interstellar medium at 43,000 miles per hour. When an object moves through a medium faster than that medium can respond, it creates a shock wave. A bow shock, like the V-shaped wave a boat makes in water, or the sonic boom of a supersonic aircraft. The heliosphere should be doing exactly this, ploughing through the interstellar medium and creating a distinct compressed region ahead of it. These scientists calculated that this bow shock should exist at around 230 astronomical units from the Sun, roughly twice the distance of the heliopause. They were so confident in this prediction that they didn't really question it. Every model included it. Observations of other star systems appeared to confirm it. Infrared telescopes had photographed stars surrounded by glowing arcs of heated gas, clear evidence of bow shocks. Our solar system should have one. The math demanded it. Voyager found nothing, not a hint of a bow shock, no sudden jump in pressure, no temperature spike, no density change. The spacecraft flew through the entire region where the shockwave should have been and recorded only gradual, gentle variations. No drama, no boundary, no evidence that any of the models were even approximately right. At first, these scientists hoped Voyager had simply missed it, that the bow shock curved around the heliosphere and Voyager's trajectory happened to pass through a gap. But as the data accumulated over years, that explanation became untenable. The bow shock didn't exist. Not in the way models had predicted, not at all. The reason turns out to be something the models had simply assumed incorrectly: the density of the local interstellar medium. For a bow shock to form, the medium has to be dense enough that the heliosphere can't part it faster than the medium can respond. But our solar system currently moves through an unusually thin region of space called the local fluff, a low-density cloud with only about 0.3 atoms per cubic centimetre. That's 100 times less dense than the denser interstellar clouds nearby. The local fluff is barely there. The heliosphere parts it without generating a clean shock wave. Instead, what Voyager found was what scientists now call a bow wave, a gradual, gentle increase in pressure and density spread across billions of miles rather than concentrated in a sharp boundary. Not a sonic boom. More like the gentle pressure wave you might feel standing in front of a slowly moving train. This discovery carries a profound implication. The properties of our protective bubble change dramatically depending on where we are in the galaxy. When our solar system passes through denser interstellar clouds, which it has done before and will do again, the bow shock reappears, the heliosphere compresses, and Earth's radiation environment changes. We happen to be living in an unusually sheltered moment in cosmic history. That will not always be the case. One of the most scientifically valuable aspects of the Voyager program, and one that was never specifically planned, is the fact that two spacecraft crossed the heliopause from completely different directions and found completely different conditions on the way out. Voyager 1 travelled upward, out of the plane of the solar system, through the region closest to the nose of the heliosphere, the compressed leading edge that faces our direction of travel through the galaxy. Voyager 2 travelled downward and slightly to the side, exiting through a region closer to the flanks. The differences in what they recorded are striking. Voyager 1 saw a gradual, months-long build-up in cosmic ray levels before the final sharp jump at the heliopause. Voyager 2 saw a much more abrupt transition. Cosmic ray levels jumped almost suddenly, with very little warning. Voyager 1's magnetic field showed no rotation at crossing. Voyager 2's showed a clear 45-degree shift over several days. Voyager 1 encountered some of the hottest plasma temperatures ever recorded at its crossing, exceeding 250,000 degrees. Voyager 2's boundary plasma was considerably cooler, around 100,000 degrees. Even the thickness of the transition zone differed. Voyager 1 spent about a month crossing a turbulent region of mixed solar and interstellar influences. Voyager 2 crossed a much sharper boundary in only a few days, suggesting the heliopause was more compressed and better defined in that direction. Scientists spent years working through the implications, and some of the differences could be explained by position. The nose region that Voyager 1 passed through is subject to more intense compression than the flank region Voyager 2 exited through. But some differences had to be explained by timing. The two crossings happened 6 years apart, 6 years during which the Sun's 11-year activity cycle had progressed significantly. The heliosphere was larger and more extended during Voyager 1's crossing near solar maximum. It had contracted during Voyager 2's crossing near solar minimum. What the comparison ultimately showed is that the heliopause is not a fixed, stable boundary that you can simply describe once and be done with. It is a dynamic, constantly evolving interface that varies enormously across its surface and over time. And any future mission crossing the heliopause will encounter unique conditions, shaped by exactly where and when it happens to cross. 2 data points is a beginning, not a complete picture. The full 3-dimensional structure of the heliosphere remains largely unmapped. To truly understand it, scientists will need spacecraft measuring it from dozens of different directions, transmitting data for decades. What Voyager gave us is something invaluable: a proof of concept, a baseline, and a set of questions so specific and so surprising that they will drive solar physics research for the next century. Let's take a moment to appreciate the sheer scale of how wrong the predictions were, because there's something important in that wrongness. The termination shock was predicted at 90 astronomical units. Voyager 1 found it at 94. Voyager 2 found it at 84. A 10-unit discrepancy between 2 spacecraft crossing the same boundary. Models simply didn't account for the heliosphere's asymmetry. Cosmic ray levels were predicted to rise smoothly and continuously as Voyager moved outward. Instead, they rose in distinct steps with plateaus between them, revealing the magnetic highway, a region nobody had imagined existed. The heliopause was predicted to be a thin, relatively clean boundary, perhaps a few million miles thick. Voyager found a transition zone stretching hundreds of millions of miles, turbulent and chaotic and wildly active. Temperatures near the boundary were predicted to be lower than those inside the heliosphere. Instead, they were dramatically higher, driven by compression and magnetic reconnection on a scale the models had severely underestimated. The bow shock was predicted to exist at around 230 astronomical units. It doesn't exist at all under current conditions. The magnetic field was predicted to rotate clearly when Voyager crossed into interstellar space. Voyager 1 detected no rotation, and the reason was a cosmic coincidence so unlikely it's still a little hard to accept. The heliosphere was predicted to be roughly spherical. It's actually compressed, asymmetric, possibly tail-fragmented, and constantly changing shape in response to forces nobody had fully modelled. What does this track record of failure tell us? Not that the scientists were incompetent. It tells us that the universe is genuinely more complex than our models, and that the only way to find out what's actually out there is to go there. Every failed prediction is a discovery. Every surprised instrument reading is a window into reality that no equation, no matter how elegant, could have opened on its own. The revisions that followed Voyager's data have produced a generation of more sophisticated heliosphere models. Models that include magnetic reconnection, account for asymmetry, incorporate time dependence, and treat the local interstellar medium as the complex, structured environment it actually is. These models are better, but scientists are also more humble now about how much they don't know. The universe doesn't care about our assumptions, it just keeps doing what it does. And our job, as scientists and as a species, is to keep sending machines into the dark until reality finally shows itself. Pause for a moment and consider what it actually means that Voyager is still working. The onboard computer has 68 kilobytes of memory. Your smartphone has billions. The data transmission rate is 160 bits per second, slower than the dial-up modems that were considered embarrassingly primitive in the late 1990s. The instruments were designed using technology from before personal computers existed. Some of the circuits use vacuum tubes. The transistors were hand-soldered. And yet, after nearly 5 decades in the most hostile environment imaginable, vacuum, extreme cold, constant radiation bombardment, micrometeorite impacts, zero maintenance, zero repairs, both spacecraft are still transmitting, still measuring, still teaching us things we didn't know. The secret to Voyager's longevity is a combination of engineering philosophy and sheer good fortune. The philosophy was simple: over-engineer everything, use proven, robust materials, avoid exotic technologies, If something simple works, use the simple thing. Build in redundancy at every critical point. Design systems to fail gracefully, not catastrophically. The power comes from radioisotope thermoelectric generators, devices that convert the heat of decaying plutonium-238 directly into electricity. No moving parts, no chemical reactions that can exhaust themselves, just physics, steady and reliable. At launch, the generators produced 470 watts. They now produce around 250 watts, declining at 4 watts per year as the plutonium slowly decays. Mission engineers face a constant, unwinnable war against this power decline. Every instrument on Voyager draws power: the cosmic ray detector, the plasma sensor, the magnetometer, the heaters that prevent critical systems from freezing, the radio transmitter. Together, they need more power than the generators can currently produce. So the team shuts things down one by one, buying years of life for the remaining systems at the cost of the silenced ones. In 2017, one set of attitude control thrusters, the tiny rockets that keep Voyager's antenna pointed at Earth, showed signs of degradation from decades of residue buildup. Engineers activated backup thrusters instead, thrusters that had not fired since 1980. 37 years dormant. They worked perfectly. The transmitter uses a travelling wave tube amplifier, a vacuum tube design that happens to be highly resistant to radiation damage. This is why, after 40+ years and billions of cosmic ray impacts, the transmitter still works. Every day, it fires a signal of 23 watts into space, less power than a refrigerator light bulb. And that signal travels 13 billion miles to reach Earth, arriving so faint that only the giant 70-meter dish antennas of NASA's Deep Space Network can detect it. The signal takes over 21 hours to arrive. Every command sent to Voyager takes another 21 hours to confirm. Total response time for any problem, 42 hours. 2 full days between discovering an issue and finding out whether your fix worked. This is what deep space operations actually look like, not the frantic real-time drama of science fiction, but long, patient waiting, careful planning, and the humbling acceptance that you cannot intervene quickly when something is that far away. Voyager will eventually go silent. Around 2035, the generators will drop below the threshold needed to power any instruments. Controllers will make the final decision about which systems to keep on longest. Eventually, even the transmitter will fall silent. And somewhere in the dark, a machine built by human hands in 1977, carrying a golden record with the sounds of whales and Beethoven and Chuck Berry, will keep moving through interstellar space at 38,000 miles per hour. Forever. Now Voyager is out there, in interstellar space. And the data it's sending back is revealing something that surprises even the scientists who have been working with it for decades. Interstellar space is not empty. It's not uniform. It has texture. The local interstellar medium, the material between stars in our immediate galactic neighborhood, contains filaments and knots and voids. Some regions are denser with hydrogen gas. Others are nearly hollow. Temperature varies by tens of thousands of degrees over distances measured in light years. Magnetic field strength changes by factors of 2 or 3 across the same distances. Our solar system currently sits inside something called the local cloud, a small, relatively cool, relatively dense region of gas within a much larger structure called the local bubble. The local bubble is a cavity roughly 300 light-years across, carved out millions of years ago by multiple supernova explosions. The interior of the bubble is hot, around 1 million degrees, and extremely thin. The local cloud is like a pocket of fog inside this enormous hot cavity, cooler, denser, different. In 10,000 to 20,000 years, our solar system will exit the local cloud and enter the hotter, in thinner bubble interior. When that transition happens, the heliosphere will dramatically expand. Without the cloud's pressure pushing inward, the solar wind will inflate our protective bubble to perhaps twice its current size. Cosmic ray levels reaching Earth will drop as a result of the expanded shielding, but transitions in the opposite direction have also happened. Around 10,000 years ago, our solar system entered the local cloud from the other side. At that moment, the heliosphere shrank. Cosmic rays increased. Some scientists have proposed, still controversially, that this may have contributed to climate changes at the end of the last ice age by increasing atmospheric ionization and cloud formation. There is a larger pattern at work here, visible over millions of years of our solar system's galactic journey. As we orbit the center of the Milky Way, completing one full circuit every 230 million years, we pass through different regions of the galaxy with very different properties. Dense molecular clouds, empty voids, spiral arms dense with newly forming stars and frequent supernovae. Each environment has different interstellar medium density, different cosmic ray flux, different magnetic field strength, and each environment shapes the heliosphere differently. Some scientists have proposed that passages through the dense spiral arms of the Milky Way, which happen roughly every 30 million years, correlate with the mass extinction events in Earth's fossil record. The mechanism would be elevated cosmic ray flux compressing the heliosphere, increasing radiation at Earth's surface, affecting cloud formation, altering climate, and ultimately stressing ecosystems beyond their tolerance. The evidence is suggestive but not conclusive. What Voyager is doing by mapping the current state of the interstellar medium with unprecedented precision is building the foundation of data needed to eventually test hypotheses like this properly. We are not just machines drifting through empty space. We are living inside a dynamic, structured cosmic environment that has shaped the history of life on this planet, and will continue to shape it long after we are gone. Of everything aboard Voyager, the Golden Record is the most profoundly human. It is a 12-inch gold-plated copper disc sealed in an aluminum protective cover, carrying 90 minutes of audio and 116 encoded images representing life on Earth. Music from 27 different cultures, spanning thousands of years of human expression. Beethoven's Fifth Symphony, a Pygmy Girl's initiation song from Zaire, a Navajo night chant, Peruvian panpipes, Japanese shakuhachi flute, Bach's Brandenburg Concerto, and Chuck Berry's Johnny B. Good. Natural sounds: thunder, wind, rain, surf, crickets, frogs, the calls of birds, the songs of humpback whales. Spoken greetings in 55 languages, from ancient Sumerian to modern Mandarin. And images, mathematical equations, diagrams of DNA, human anatomy, animals, landscapes, cities, food, family. The instructions for playing it are etched on the cover in a visual language designed to be decipherable by any sufficiently advanced civilization. Diagrams showing the record spinning at the correct speed, the stylus tracing grooves, the binary encoding of images, the hydrogen atom as a universal unit of measurement. Carl Sagan led the team that assembled it, and the process forced an impossible question. How do you represent all of humanity in 90 minutes? What do you choose? What defines us? The choice is made: music over conquest, diversity over uniformity, nature alongside technology, birth and family and wonder. Say something profound about what the people who made those choices believed was most important about being human. There is a spoken message from President Jimmy Carter on the record. It includes these words: "We are attempting to survive our time so we may live into yours." That line lands differently every time you hear it. When Voyager launched, nuclear war was a constant looming possibility. climate change was barely on the radar. And yet the people who built Voyager sent it into space carrying a record of what humanity was, because they feared humanity might not last. That fear has not diminished. The record will outlast almost everything else on Voyager. Long after the instruments fail, after the transmitter goes silent, after the structure slowly erodes over billions of years of cosmic ray bombardment, the gold-plated disk will survive essentially intact. Gold does not corrode in vacuum. Radiation will eventually damage it at the molecular level, but this takes billions of years. The record is designed to remain playable for at least 1 billion years, possibly longer. The odds of anyone ever finding it are, mathematically, essentially zero. Space is too vast. Voyager is too small. In 40,000 years, it will pass within 1.6 light-years of a star called Gliese 445. Not close enough for gravity to capture it, not close enough for any planet's inhabitants to notice it, if any inhabitants exist. It will sail past in the dark. The critics who pointed out the absurdity of the golden record were right, in a narrow sense. Any civilization capable of intercepting a spacecraft in interstellar space would have technology so far beyond ours that a copper disk with a diamond stylus wouldn't tell them anything they couldn't deduce from first principles. The record was never really for them, it was for us. It was the act of making it that mattered, of sitting down and asking, what are we, really? What do we value enough to send into forever? The record doesn't answer that question, but the act of asking it, the seriousness with which a group of human beings tried to represent all of humanity in 90 minutes, says everything about who we are and what we hoped we might become. And somewhere, right now, 13 billion miles away from everything we have ever known, the record is drifting through the dark, sealed and silent, carrying the sounds of whales and laughter and Beethoven into a universe that may or may not contain anyone who will ever hear them. We sent it anyway. That is enough. The end is coming. Not dramatically, not suddenly, but with the quiet inevitability of physics. Every year, Voyager's power output drops by 4 watts. Every year, the team shuts down another heater, powers down another instrument, and makes another impossible choice about what to sacrifice to keep the most critical systems alive a little longer. The engineers who make these choices have worked with Voyager for decades. Some have spent their entire careers with these spacecraft. When they shut down an instrument, knowing it will never turn on again, knowing that whatever it might have detected in the years ahead will now remain unknown forever, they feel it. By approximately 2030, Voyager will likely no longer be able to run heaters for its instruments. Without heat, components begin to fail, lubricants freeze, materials become brittle, electrical connections degrade. Some things will survive longer than their rated operating temperatures. Some won't. Engineers have already been surprised multiple times by systems performing well below their design limits. There may be more surprises ahead. The absolute deadline is around 2035. By then, the generators will produce too little power to operate any scientific instruments. The final act will be to shut down everything except the transmitter, keeping it alive on minimum power, broadcasting a carrier signal that carries no data, just a tone, a heartbeat. I am still here. This configuration might extend operations by a few additional years, and then one day the signal will fade. Ground controllers will watch the signal strength decline on their monitors over days or weeks, knowing what it means. They'll keep the Deep Space Network antennas pointed at Voyager's last known position, waiting, listening. After a month of silence, NASA will officially declare the mission ended, but Voyager won't stop. The spacecraft will keep moving at 38,000 miles per hour, carrying its golden record through interstellar space for millions of years, long after the civilization that built it has transformed into something unrecognizable or ceased to exist entirely. It will outlast our buildings, our languages, possibly our biology. It is already the most enduring artifact of human civilization. In 40,000 years, it will pass near Gliese 445. In 300,000 years, another star. Over millions of years, gravitational interactions with the stars it passes will slowly alter its trajectory. Not enough to capture it, just enough to redirect it, slightly, across geological ages of time. It will orbit the galactic center as we do forever, or until something improbable happens. If future humanity, or some other civilization, ever develops interstellar travel, retrieval would be possible in principle. Voyager's position can be calculated with precision for millions of years in advance. Finding it would require will, not math. Returning it to Earth, or whatever Earth becomes, would be one of the great acts of archaeological preservation in history. A time capsule from the species that first left its home system, now retrieved by the species that species became. None of that may happen. Voyager will probably drift in silence forever, unreachable and unknown. But right now, today, it is still talking to us. 160 bits per second, 21 hours of delay, a whisper from the edge of everything. And the team that has been listening for nearly 50 years is still there, still at their monitors. I'm still writing down what it says. Make sure you appreciate it while it lasts, because the silence, when it comes, will be permanent. Voyager gave us 2 data points, 2 trajectories through the heliopause, separated by a few degrees in direction and 6 years in time. It gave us the first direct measurements of the interstellar medium, the first detection of interstellar plasma oscillations, the first in situ measurement of the galactic magnetic field. It overturned a generation of theory and built the foundation for the next generation. But 2 data points are not enough. The heliosphere is a 3-dimensional structure that varies across its entire surface and changes over time. Understanding it properly requires measurements in dozens of directions, over multiple solar cycles, with instruments built for interstellar science rather than adapted from instruments designed for the Jovian system in 1970. NASA has studied concepts for a dedicated interstellar probe for years, a spacecraft designed specifically to study the heliosphere and the local interstellar medium, flying faster than Voyager, reaching the heliopause in 15 years instead of 40, carrying modern instruments optimized for exactly this science, targeting a specific direction to complement Voyager's trajectories. Such a mission would answer questions that Voyager raised but cannot resolve. The true 3-dimensional shape of the heliosphere, the structure of the heliopause across its entire surface, the extent of the bow wave, the nature of the heliotail. The challenge, as always, is resources and will. Voyager cost roughly $800 million in today's money, astonishingly cheap for what it delivered. An interstellar probe would cost several billion. It would require decades of commitment from institutions and governments. That commitment is not guaranteed. Meanwhile, Voyager continues to provide data that no other instrument can replicate. There is no telescope, no remote observation, no Earth-based experiment that can tell us what the interstellar medium actually feels like from the inside. Only Voyager is there. Only Voyager has been there. And every day it keeps transmitting is a day we learn something new about the environment our solar system occupies. The universe, it turns out, is not the cold, static, empty void that common sense suggested. It is alive with energy, structure, and processes that span light years. It hums, it breathes, it pushes back. The boundary between our solar system and the rest of the galaxy is not a wall. It's a battlefield where 2 cosmic environments have been fighting for dominance since before our planet formed. And 2 small machines, built by human hands in the 1970s, flew through that battlefield and came out the other side, still talking, still measuring, still surprising us with every transmission. That is one of the greatest things our species has ever done. And we are lucky to be alive in the brief window of time when the signal is still coming through. If you made it to the end of this video, thank you, genuinely. Drop a comment below with the thing that surprised you most. Subscribe if you want more deep dives like this one. And until next time, keep looking up.